on location for many days, the men on this rig have made a lot of holes. The hole provides a way for oil and gas to be withdrawn from far beneath the surface. But before even 1 foot of hole was drilled, the well had to be planned. Men from the operating company, the company that owns the rights to the oil and gas, considered many factors. One factor was the formations to be drilled. A cross-section of the earth shows that the formations lie one on top of the other, like a layer cake. Some of these formations present problems that must be overcome. For example, as in the circle, a formation near the surface caves in and creates a tight spot in the hole. Another formation contains fresh water that a nearby town uses for drinking water. It must be protected from contamination. Another formation below contains salt water. This salt water could pollute the freshwater zone above. Something must be done to overcome these problems. So drilling comes to a temporary halt in a formation that is made up of good, firm rock. This hole will be lined with a special kind of pipe called casing. Here the casing is laid out on a rack at the rig. These individual lengths, or joints of casing, will be screwed together and run into the hole. Then cement is placed around the casing. The cemented casing protects the freshwater zone. Also, the cement supports and protects the casing. After the first or surface string of casing is cemented, drilling starts up again. The drill passes through many formations. Some give problems that call for casing and cement. Maybe a shale is encountered that swells and sloughs off into the wellbore, making it hard to keep the hole clean. Here's a formation that contains salt water under tremendous pressure. When penetrated by the drill, it will try to blow out, but the drilling crew will be ready for it. Another formation is made up of fractured and broken rock. Because drilling fluid could be lost to the formation, it is called a lost circulation zone. Again, the crew will be ready for it. And here is firm rock again, a good place to temporarily halt drilling. Run inside the surface string, a smaller diameter string of casing is set and cemented. The smaller string runs upward all the way to the surface, but the cement outside the smaller string may or may not go all the way up. In this case, it is not necessary. Once again, drilling continues, this time to the target, the reservoir of gas, oil, and salt water. The reservoir has oil with gas on top and salt water underneath. Neither the gas nor the water should be produced with the oil. To prevent water and gas production, casing and cement is used again. A third string of casing, called the production string, is set and cemented through the reservoir. Perforations are made to allow only the oil to flow into the production casing. The gas and water are kept out. So casing and cement is needed to prevent caving in the hole, protect freshwater zones from pollution, exclude water from the producing formation, and permanently seal off high-pressure zones, zones of lost circulation, and other troublesome formations. Now let's see how casing and cementing operations are carried out. First, here's the drilling assembly in the hole. Before the casing is run, the drill stem will be removed, leaving the hole full of mud. But it is important to circulate first so that the hole and mud can be put in good condition to receive the casing. All or most all of the cuttings need to be circulated out. Any thick portions of solid mud, wall cake, need to be circulated out as much as possible. And during circulation, the mud engineer tests the mud. It should be the proper thickness or viscosity, the right weight or density, and so on, to make it as easy as possible to run the casing and get a good cement job. Once the hole and mud are conditioned, the crew trips out the drill stem. Then the first joint of casing is raised into the derrick. Often special pieces of accessory equipment are attached to the casing. These accessories aid in obtaining a good cement job. This round nose device, called a guide shoe, is installed on the first joint of casing. Thread locking compound is used on the threads to keep the shoe from coming unscrewed. A cross-section of a regular guide shoe shows that it is a heavy collar with a round end. It guides the casing into the hole. Also, it has an opening in the bottom to allow drilling mud to enter the casing as it is lowered in. Later, cement exits through this opening. Sometimes, instead of a regular guide shoe, a float shoe is used. As the casing is lowered into the mud-filled hole as it left, the mud cannot get past the closed valve. However, as at right, the valve opens when mud is put into the casing. A float shoe makes it possible to float casing into the hole to ease some of the load on the rig derrick. If the casing is empty and there is drilling mud in the hole, then the casing tends to float, much like a boat floats in water. Since some of the weight of the casing is floating, then some of the strain on the derrick is eased. But one thing to watch: if, as at left, the casing is allowed to remain totally empty, then the pressure of the mud in the hole could collapse the casing. Therefore, as at right, mud is added to partially fill the casing to keep it from collapsing. The idea is to keep enough mud inside to prevent collapse, but not so full as to lose flotation. An automatic or differential fill-up shoe is sometimes used. It automatically regulates the amount of mud in the casing. At first, the valve in this shoe keeps mud from getting into the casing, but only to a point. As the casing and differential fill-up shoe get deeper and deeper into the hole, as at left, mud pressure causes the valve to open and mud enters the casing. However, as at right, the mud pressure in the casing finally closes the valve. The valve closes before the casing is completely filled, so all the flotation won't be lost. When the casing string lengthens and goes deeper into the hole, as at left, the valve opens again, allowing more mud in, until, as at right, the valve again closes. This opening and closing is repeated as the casing is run. In addition to whatever type of guide shoe is used, a device called a float collar is also often used. The man in the background is applying thread locking compound to the float collar. The float collar may be installed on top of the first joint or on top of the second or third joint to go in the hole, depending on hole conditions and other factors. A float collar is similar to a float shoe. Mud cannot get past the valve and into the casing because the valve closes. This allows the casing to float. However, mud and cement can be pumped through the valve because it opens with pressure from above. Incidentally, there are also automatic fill-up collars available that work like the automatic fill-up shoe seen earlier. This man is installing a centralizer on the casing. Centralizers help center the pipe in the wellbore by keeping the casing off the side of the hole. This allows cement to seal and provide a good bond. Scratchers are also installed on the casing. This is a reciprocating scratcher, which means that the casing string has to be moved up and down for the scratcher to work. Scratchers remove some of the wall cake so the cement can bond better on the walls of the hole. This is a rotating scratcher. The casing string must be rotated for the scratcher to work. Hole conditions determine which type of scratcher to use. Casing should not be lowered into the hole too fast. 1,000 feet per hour might be a good maximum speed. However, if there are formations that fracture easily, slower running speeds are necessary. Do not create pressure surges. Casing in a wellbore is a lot like a piston in a cylinder. The faster the piston moves through the cylinder, the more pressure is built up. If one of the formations is weak and fractures easily, pressure surges could break down the formation, mud could be lost, and an expensive, time-consuming problem would have to be corrected before operations continue. As the casing is made up and lowered into the hole, and if an automatic float shoe or collar are not being used, drilling mud is added from the surface. We want the casing to float, but we sure don't want it to collapse. With the entire string of casing run, we're almost ready to cement. Here, the lowest part of the casing string and accessories are near bottom. Next step is to circulate and condition the hole. So up on the floor, a device called a cementing head or plug container, the dark red device at top center, is made up on the top joint of casing that is hanging in the elevators. The cementing head provides a connection from the mud pumps so that mud can be circulated. It has other uses, as we'll see as we go along. While circulating, let's look at the casing and accessories in the wellbore. Starting from bottom are the guide shoe, centralizer, and scratcher. Above are the float collar, more centralizers, and scratchers. Mud is circulating down the casing and up the hole. The centralizers are keeping the casing off the sides of the hole, and as the casing is moved up and down, the scratchers are removing some of the wall cake to improve cement bond to the formation. With the hole conditioned, about 10 to 50 barrels of water or special chemical spacers or flushes are pumped in. The water or chemical helps to remove wall cake and acts as a spacer between the mud and cement. With the spacer, the mud won't be likely to contaminate the cement. The trucks carrying the needed amount of dry cement are in position on this land rig. Of course, offshore, or in a marshy location, boats and barges are used. Or sometimes the bulk cement is stored in large bins at the rig. Also, the special cementing unit, truck-mounted for this land job, is made ready. 2 pumps are provided on this unit, one for pumping water to mix with the dry cement, and the other to pump the mixed cement into the well. Speaking of water, the quality of the water should be good, clear, and free of salt. If you can drink it, it's probably okay for mixing. However, seawater is used offshore with good results. The water's temperature is a consideration. Hot water may thicken the cement slurry, making it set too fast. Cold water may retard or increase the set time or freeze up in a line during winter operations. There are many additives that can be used in the cement to offset temperature problems and other problems that may occur on a particular job. The cementing service company can tailor the cement to meet various requirements. In any case, the dry bulk cement is fed out of the container and into the hopper of a mixing device called a jet mixer. In the jet mixer, as enlarged in the circle at right, a stream of high-pressure water from the pumping unit is directed at the base or throat of the hopper. Dry cement is fed from the hopper into the water jet. As the cement enters the jet of water, it is thoroughly mixed as it moves down the discharge pipe. The mixed water and cement, the slurry, is discharged into one side of a mixing tub. The inlet line to the pump on the cementing unit is placed in the other end of the tub. The pump picks up the slurry and sends it through a discharge line. The discharge line is connected to the cementing head or plug container on the rig floor. Also placed in the cementing head are a couple of devices not mentioned before: a bottom wiper plug and a top wiper plug. The first plug to go into the cementing head is the bottom plug. It wipes mud off the inside of the casing and keeps the mud separated from the cement. Notice the diaphragm. In a moment, we'll see what it's for. The top plug follows the cement into the casing and wipes cement off the casing. Also, it reduces the mixing together of cement and the mud behind the cement. This plug is solid. As the cement slurry from the pump discharge, entering from left, reaches the cementing head, the bottom plug starts down the casing with slurry behind it. When the bottom plug reaches the float collar, it stops. Pump pressure increases and ruptures the diaphragm in the plug. The slurry goes through the open valve in the collar, out the guide shoe, and into the annular space between the casing and hole. Meantime, the casing string is being reciprocated or rotated to help displace the mud. Usually, the cement slurry is pumped with enough pressure to create turbulent flow. Under turbulent flow, eddies and currents help move all the mud out and help remove uncirculated mud and wall cake by scouring. The familiar mud balance can be used to check the weight of the cement slurry as it is pumped. Sometimes an automatic weighing device is used if greater accuracy is needed. Once the calculated volume of cement has been pumped, a retainer pin is pulled to release the top plug from the cementing head. The top plug is followed by drilling mud. When the top plug seats or bumps on the bottom plug at the float collar, pump pressure increases, since no fluid can get past the solid top plug. This signals that all the cement slurry is displaced from the casing above the top plug. After the top plug bumps, the pump is shut down and pressure on the casing is bled off. With the pressure released in the casing, the valve in the float collar closes to keep cement from backing up in the casing. Pressure on the casing should be released before the cement sets. As it left, pressure causes the casing to bulge. If, as at right, the cement is allowed to set and then the pressure is released, the casing pulls away from the hardened cement, loosening the bond. After bleeding the pressure, the time comes for waiting for the cement to harden. This is called waiting on cement, or just WOC. Through the years, WOC time has been reduced. Back in 1903, there was a wait of 28 days before operations continued. In 1930, the time was reduced to 3 days. By 1945, to 24 hours. And in 1957, rig operations were studied to see if WOC regulations could be reduced still more. As a result of the studies, present-day WOC time can be as low as 6 to 8 hours in winter and 3 to 6 hours in summer, provided that good practices are followed and state regulations allow it. WOC time gives the cement enough time to set and be strong enough to bond and anchor the casing. Also, the cement must be able to take the shocks of subsequent operations, like drilling out. Zones must also be sealed off to prevent fluid in the zones from moving out. WOC time varies from state to state because of state regulations. In addition to regulations, Operators rely on their own experience. Also, the casing must be landed. The top joint of casing is suspended in a hanger inside the casing head at the surface. In most cases, casing should be landed in the head as cemented. That is, the casing is landed without slacking off or picking up on the casing. The casing hanger supports the same weight as the elevators. Once landed, the blowout preventers are attached to the casing head. Then, after WOC time, the casing and cement is pressure tested. This is just a matter of using the mud pumps to pressure up to a desired amount, say 1,600 pounds per square inch, and holding the pressure for 30 minutes. If the pressure drops no more than about 50 pounds per square inch, then the job is satisfactory. Also, it is usually necessary to find the top of the cement to make sure the cement has been displaced properly. In this case, the top should be at 5,650 feet. To locate the cement top, an instrument is lowered into the well to make a temperature log. The temperature is recorded on the bottom of the chart and depth is recorded on the left vertical line. Starting at top, at 5,500 feet, the curve increases gradually with depth. But about halfway down, at 5,650 feet, the curve shows a sudden temperature increase. This is the top of the cement, because as cement sets, it gives off heat. So, from the log, the actual cement top is where it was expected to be. On the other hand, if the actual top came out considerably below the expected top, then perhaps a large washed-out section took a lot of cement to fill. If the cement top is too low, maybe allowing formation fluid to enter the annulus above the cement, then a remedial cement job is needed. Another problem occurs when the actual top comes out higher than the expected top. In this case, as in the circle, the cement channeled around gel drilling mud, leaving an uncemented area where fluids or gas may communicate between zones. In conclusion, cementing is a critical operation. It calls for careful planning, selection of the proper cement, casing, equipment, and good techniques. Close cooperation between the operator and the cement servicing company is essential.